Right. So we're starting the next section today on integral representations of and differential equations. So the idea here is we spent the last 11 lectures building up some technology, and this was largely the technology of integral transforms, and integral transforms give us a way of understanding functions by writing them down as integrals. Sometimes we do these integrals, sometimes we can't do the integrals, and the standard integrals are great, but we can't do the integrals. Then what we have is what's called an integral representation of the function. Sometimes the integral representation of the function is all I really need in order to understand the function in various circumstances. Okay. Today I want to take that technology and use it. We want to essentially use it to understand how to solve differential equations. And if you follow the general philosophy of this course, we would like to do as little work as possible. I don't want to give you differential equations and say, well, here's a differential equation, solve this differential equation. And because these days, God invented Mathematica, and plug it into Mathematica, and it will solve the differential equation for you. So the point is not to solve particular differential equations. The point is to understand the structure underlying these differential equations. We want to extract universal properties of these differential equations and give you a toolkit that will allow you to solve a bigger class of problems than just one differential equation after the other. Okay. To that end, we're going to look at differential equations in a way that's possibly not familiar to you as applied mathematicians or physicists, but which mathematicians tend to look at differential equations this way. So again, the point is not to solve any particular differential equation. The point is to understand what's going on with a set of differential equations. And that's to view differential equations as operator equations, essentially eigenvalue problems. Okay. And the nice thing about viewing anything as eigenvalue problems, you can tend to bring as much linear algebra as you know to the problem. So that's what we want to do. So we're going to solve differential equations by giving integral representations to their solutions. And I'm going to, of course, show you how to extract information from that integral representation. Yes, properties of the solutions, what they look like, how they combine with other solutions, etc. All of which can be read from the fact that I can write the solution down as a formal integral, which I may not be able to actually do. Right? But even as mathematical physicists, we don't need to do the integral all the time. All right. And this will hinge on the fact that we can view the differential equation as an operator equation, as an operator eigenvalue problem. Okay. So this is perhaps a new way of looking at problems, and I'll show you today how we can in fact solve the quantum harmonic oscillator problem without doing any integrals at all. Okay, without, it's a differential equation, it's a second order differential equation. Ultimately, and for those of you who learn quantum mechanics, you know that the solution can be written down as coming polynomials. I'll show you how these coming polynomials arise, and we will not solve the differential equation. Okay, we will view the problem as a linear algebra problem. And we will solve that. Okay, but before we start, I need to tell you a little bit. I need to remind you. I don't exactly know what you guys have done. Who put you boundary value problems? Yes. Yes. Who taught you boundary value problems? Did you study boundary value problems as operator equations? To the power of something. No. As a differential operator acting on some function, study the differential operator. No. Okay. All right. So it's not a typical way that you would approach these problems, but when I taught the boundary value problems, that's how I taught it. So that this was essentially just a quick review of this. So I'll take a little bit of time to just tell you how to think about operators, and in particular, what we want to focus on is not just the properties of the operators, but how those operators are related to this spectrum, to the eigenvalues. And then we'll apply all of that to study the spectral problem of the harmonic oscillator. All right, good. So let me just remind you then about the kinds of operators that we're talking about. So for the most part, we're going to be interested in some adjoint operators. Okay. Now you might be familiar with the idea of an adjoint from linear algebra, where the adjoint of a particular matrix, A, we normally call A dagger, and you get A dagger by taking the transpose and complex conjugating it. Okay, that's certainly how I learned when I first learned about conjugation. But if you're coming from an analysis point of view in mathematics, you would understand that you can only define the adjoint of a matrix, the adjoint of some operator, some linear operator, with respect to a particular inner product. So if I give it a space, and define an inner product in that space, then I can define the adjoint operator. So I'm going to make all of these things clear to you. Now, the point is that how do I write this? Sorry. Linear operator A on the vector space out to the end, just as an example, acts as a matrix acting on some vector X, where this guy lives in onto the end, to give a new vector, which I'm going to call AX. So the point here is that this is some vector in onto the end, and this is some other vector in onto the end. I'm going to assume that the dimensions of A is appropriate for the problem, right? So we're thinking about finite dimensional vector spaces here. This is some n by n matrix. This is some n by 1 column vector, and this is an n by 1 column vector. This is also a vector in fact, let's make it a little bit more general than this. Let's make this vector space make some vector space Mn, meaning some n-dimensional vector space, with possibly complex value x's as well. Sure. So the adjoint of A is matrix A dagger defined the following way. if I take x prime and I take the inner product of x prime and ax, this is the same as a dagger of x prime. Okay, so this is how you technically define the adjoint in a finite dimensional vector space. What we'll see is that effectively, in terms of operators in an operator space, where this guy is now an element of the Hilbert space, this amounts to integration by parts. Okay. So I will show you what's. But the nice thing about okay, if so A is called self-adjoint, for emission, context of differential operators. If A and A dagger are the same thing. Here's the statement I want to make. Any self-adjoint operator with respect to some inner product has a complete set of mutually orthogonal eigenfunctions. A self-adjoint operator, let's call it T, on say respect with respect to some inner product possesses a complete, and I mean complete in the sense that we've been using up to now, which is that I can resolve the identity of this set of states. Complete set of mutually orthogonal eigenfunctions. So these eigenfunctions are complete in the sense that I can expand the identity in terms of them, or I can expand any function on the same space, function space, in terms of these eigenfunctions. Okay, and they're mutually orthogonal, which means that if I take the inner product of one eigenfunction with the other one, I'm going to get either one or zero. The set of all eigenvalues of T is called the spectrum of T. So, spectrum of the operator T is set of all eigenvalues we'll denote this thing by sigma of T. An eigenvalue of sigma of T can either belong to a discrete spectrum or a continuous spectrum. And this really depends on whether the eigenfunction, the associated eigenfunction, is normalizable with respect to the same inner product or not. Okay. So eigenvalue belongs in a discrete spectrum. It's the associated eigenfunction is normalizable. With respect to the same inner product. Otherwise, it belongs in a continuous spectrum. Okay, so sigma of t is either discrete or it's continuous, or in some examples, like the hydrogen atom, the spectrum can be partially discrete, also partially continuous. Okay. And really all is a statement about whether these eigenfunctions are normalizable or not. In other words, I define some inner product of my space, and I have these functions, the eigenfunctions, and if I calculate the norm of those eigenfunctions, and I find that it's finite, then the associated eigenvalues belong to a discrete set or a discrete subset of the spectrum. Then I say the spectrum is discrete. So if I can't normalize the eigenvalues, if I can't normalize the eigenfunctions, then the spectrum is called continuous. Okay. So today I want to focus on a discrete spectrum and see how far we can explore this idea, and then we'll talk about continuous spectrum. You get back from your vacation. Next week is vacation, right? So let's think about a discrete spectrum. So suppose sigma of t is discrete for the purposes of the rest of the spectrum. But what this means is that I can find some set of functions phi of x such that t acting on phi of x, phi n of x is active in phi of x. This is what it means for phi n to be an eigenfunction and the lambda x to be corresponding eigenvalues. So we'll assume that these n's are some set of integers. Okay, I'm also going to assume that the operator t is self-adjoint. So if t is self-adjoint, then the following is true. If I calculate the inner product between two of these guys, phi m and phi n, say, I'm acting on phi n with t to produce the vector t phi n. Okay. So I must be clear, I've now moved on from a finite dimensional vector space. In general, now I can have an infinite dimensional vector space. These things are functions. They're functions, some set of n functions that are labeled by an integer, but they're functions. So this can be a differential operator, for example, first derivative, second derivative, etc. Don't really care. Okay, the point is that it's some self-adjoint linear operator. That's all I really care about. I haven't written down the representation for it. I don't need to write down the representation for much of what I'm about to say. When we get to the harmonic oscillator, then we'll write down the representation. But suppose T is T dagger. Then if I calculate, if I subtract from this T dagger acting on 5M by M. So I essentially just move the T from there to there, it comes to the dagger, where T is equal to T dagger. These two are the same things. And this is equal to phi M T phi N minus T phi M in product phi N. This first guy is going to give me lambda n phi n with this inner product. So that's lambda n. The second guy is going to give me T acting on phi m. That's going to pull out a lambda m. And I take out a common factor of phi m inner product phi n. And this was equal to 0. There's only two ways this gets equal to 0. Either this combination is 0, or this inner product is 0. So let's make one more additional assumption. And the assumption is that the eigenvalues are non-degenerate. That means that lambda n cannot equal to lambda n if m is not equal to n. So this means that the eigenvalues are non-degenerate. Well, if that's the case, then this is not 0. If m and n are not equal to 0, which means that the only way that's going to be true is if phi m in the product phi n is equal to 0. So now I'm going to define my inner product as the integral of phi m of x bar phi n of x dx equals 0. Sorry, it's equal to it's equal to 0 if m is not equal to n and not equal to 0 otherwise. It's not equal to 0 otherwise, sorry. If it's some finite number, I can always normalize by this finite number by dividing 2 by the phi m's, in which case I might as well call this 1 otherwise. And another way of saying this is Kronecker delta n. Okay, with some appropriate scaling of these eigenvalues. Okay, so basically you compute the eigenvalues, of the eigenfunctions. Compute the eigenfunctions and calculate the inner product. If the inner product comes up to some finite number that's not 1, you redefine your inner product, your eigenfunction by dividing the square root of that, whatever that number is, and then you can take it to Completeness, on the other hand, means that if I take phi m, sorry, phi m of x, phi m n of x bar, and I sum out over the ends, then this is the Dirac delta function, delta of x minus x. So notice in this expression here, I'm integrating out all the x dependents, so the arguments here, x and x are the same. Here, I'm summing out over the n dependents, label dependents. So the argument here is x and x prime, on the right hand side, I have a delta of x minus x prime. I'll show you what the implication of this is, but basically, this is the statement that I can resolve the identity of the function space. So this gives us a representation then of the Dirac delta function. And I can use this representation of the Dirac delta function to make an expansion of any function in this function space. So to that end, suppose f of x is some function in our Hilbert space. And f of x prime delta of x minus x prime is sum over n of phi n of x f of x prime phi n bar of x prime. Remember, the phi n's are eigenfunctions of the operator t, and this is just some arbitrary function in space. Now, if I integrate out over x prime, I'll find that Dirac delta function samples f of x prime and x prime to x. So the result of f of x is f delta x prime. That's on the left hand side. On the right hand side, if I integrate out over x prime, the only thing that's going to be affected are these two guys here, which have an x prime dependence. The rest I can pull out. So the sum over n phi n x times the integral f of x prime phi bar n x prime dx prime. And whatever this is, it's a constant in the continuous variable x. Because I integrate out all the x prime dependence. This only depends on x prime, this only depends on x prime. It's going to carry an n label, but I've integrated out the x dependence. You see that? So let's just call this guy an, some set of constants an. Okay. So what have we demonstrated? We demonstrated then that this function f of x can be expanded as sum of coefficients an over the eigenfunctions phi n of x. So this is what completeness means. It means that I can expand any function in my Hilbert space in this orthogonal basis. So in words, this statement is a statement that if I can expand the delta function in the basis of eigenfunctions, then I can expand any function in one function space in that same basis. Okay, everybody happy with this? In general, then, the statement that I can make and be comfortable making is that solving the eigenfunction problem, solving the eigenvalue problem, is difficult. So my statement here was, okay, I'm stopping thinking about differential equations as some set of some differential equation that I can solve using rotating something that's stressed here. And I'm going to start thinking about it as an eigenvalue problem. And the question is, well, does it bind me? Am I going to be able to solve differential equations any easier? The answer is, in general, no, it doesn't, because solving the eigenvalue problem is difficult. Okay. However, what it is going to give us is a stronger handle a set of solutions. So while I might not be able to solve in any easier way a particular differential equation, I will understand things about the set of solutions of the class of differential equations. That's my general statement. Okay. However, that said, there are some special cases that actually occur with surprising frequency in mathematical physics, where some special tricks exist. Okay. So these are special cases, and we can use special tricks to solve these special cases. But sometimes these special cases are important enough that understanding how these special tricks work is worth our time. So to illustrate this principle of solving the problem any which way you can, I want to solve the simple harmonic oscillator, but a quantum harmonic oscillator. So the quantum harmonic oscillator is defined by the following Hamiltonian. There are very definitely other factors that enter this harmonic oscillator problem, but we don't really care because we want to approach the problem now as mathematical physicists. So I don't care about factors of H bar and masses and couplings, etc. at this point. Take away all of that, you can always define appropriate units. The Hamiltonian that defines a quantum harmonic oscillator is this Hamiltonian. Right? Minus second derivative squared plus x squared equals 0. It's quadratic because it's quadratic in the momentum and it's quadratic in the position variable. Okay. But more importantly, this the associated eigenvalue problem also known as the time-independent Schrödinger equation. Basically says that H psi, let's just make our lives easier, work in one direction, is lambda x. Right? So again, you're familiar with this as the time-independent Schrödinger equation. From the point of view of what we want to do here, so my claim is that we can use these ideas from operator theory to solve this problem without actually solving a differential equation that comes with the time-independent Schrödinger. Right? Let me show you how. First thing I will note is the following. I can write this second order differential operator as a product of two first order differential operators by factorizing it. as follows. Keep in mind that this is an operator, so if you want to show that these two are the same, you have to act on some test function with this, and you show that the test acting on the test function with this thing on the right hand side using the same thing as acting on the test function as the thing on the left hand side. That means just keeping track of derivatives and multiplication. I'm going to call this guy d by dx plus x. I'm going to call it the operator q. Now notice the following. If q is d by dx, then if I act on q with, if I use q to act on, let's say, x, and I then take the inner product, say psi, and I take the inner product with some other function phi, like this, then this is the integral of phi bar d by dx plus x acting on psi integrated with respect to x. That's what I mean by that inner product. Okay. Now take this guy, and it's acting to the right on the side. Integrate by parts, and I'm going to assume that all the boundary conditions are met so that I can ignore the boundary. Down here, I want to throw the derivative on this. If I do that, okay, let me arrange that. So this is the integral of phi bar d dx psi plus phi bar x psi dx, which is the integral of minus d by dx d phi bar by dx times psi plus phi bar plus x phi bar, or multiply psi dx. Now I can think of this thing as an operator acting on phi bar, and that operator will be minus d by dx plus x acting on phi bar times psi dx. But this is just what we want to write down as phi inner product with psi. In other words, I identify q dagger as minus d by dx plus x. So if q is the operator d by dx plus x, minus d by dx plus x is the adjoint q dagger. And in this example, you can see that the operator q is not a self-adjoint operator. Right? Okay, but what this means is that my Hamiltonian is q dagger q plus 1. So let's switch around the operator ordering. So instead of going q dagger q, let's see what happens if we act on some test function psi with q dagger. So notice that q dagger acting on some test function psi. This is d by dx plus x minus d by dx plus x acting on psi, which is minus the second derivative of psi respect to x plus psi plus x d psi by dx minus x d psi by dx plus x squared on the side. These two guys take each other out. And so this is minus d by dx squared acting on d2 by dx squared acting on psi plus x squared, and then I have this psi. So this is nothing but the Hamiltonian plus 1 acting on psi. In other words, I managed to write down what the algebra of the q's are. Okay. So one representation of the Hamiltonian, so h is q dagger q plus 1, but it's also q dagger minus 1. Everybody? So the q's satisfy the algebra. If I subtract, if I go q dagger q minus 1 minus q dagger q dagger minus 1 is the same as q dagger q plus 1. I take the q dagger q on the other side, I'll have a q dagger minus q dagger q, that's commutated. I have a plus 1 on the right hand side and a minus 1, take minus 1 over the 2. Okay. So that's the algebra satisfied by these operators. These bosonic operators, because they satisfy the commutated algebra. We'll see a little later on that we can define an algebra with anti-commutators, in which case we'll be talking about a fermionic operator. But I didn't just want to recast the Hamiltonian. I've already made some progress there because this problem becomes one of working with first order differential operators rather than second order differential operators, and that's progress. But in fact, I can do more. I can actually solve the entire Harmonic oscillator problem. Write down the general solution of the quantum harmonic oscillator. Let me show you how that works. First thing we know is the following. Suppose that I have some eigenfunction of q dagger q. Suppose I have some eigenfunction of q dagger q with non-vanishing eigenvalue now. So suppose that psi is an eigenfunction of q dagger q with eigenvalue lambda, and I want to assume that lambda is non-vanishing. So what does this mean? This means that q dagger q acting on psi is lambda psi. But this also means that if I act on this equation with another q from the left, that q dagger q psi is q on lambda psi. But this lambda is just lambda, so I can exchange these two. That's equal to lambda acting on, so lambda times q psi. And this bracket is associative, so it's associated with that product. Now I have a statement that the operator Q dagger acting on the function Q psi is lambda times the function Q psi. In other words, Q psi is an eigenvalue of Q dagger with the same eigenvalue, sorry, it's an eigenfunction of Q dagger with the same eigenvalue lambda. So this is an eigen function of Q dagger, also an eigenvalue. And if that's the case, because these lambdas are the same, with the exception of a possible 0, because I've excluded lambda equals 0. So with the exception of something going on with the 0 mode, so the eigenfunction with eigenvalue 0, these two operators, Q dagger Q and Q dagger, will have the same spectrum. Okay. But it turns out that actually, as an operator acting on functions with an L2 norm on the whole real line, there is actually a problem with the 0. So here's the possible exception of a 0 mode. And 0 mode is an eigenfunction of eigenvalue 0. Q dagger and Q dagger Q. Right, let's use our notations. Spectrum of Q dagger is the same as spectrum of Q dagger Q. So the question then is, should we be concerned about this? The answer is, for our problem, the harmonic oscillator problem, yes, we actually should be concerned about this. So the first question is, are there any zeros? And the answer is yes. In fact, if I had to ask you to guess some function, some non-trivial function, so 0 is obviously a trivial function. If I asked you to guess some non-trivial function that when you act with Q would give you a 0 eigenvalue without doing any analysis, you just make a guess. What did you guess? I'm looking for an eigenfunction of the operator Q, this line, that will give me a 0 eigenvalue. Minus x.
So minus x squared. Minus the half.
But if I differentiate minus half x squared, I get something that's like x, and if I multiply it with x, then I get something that's like it's q. What's the current state of the world? Good. So, just to make this simple, I'm looking for a function which, if I take a derivative of that function, it's proportional to the function itself with a factor of x sitting in front, and a minus sign. So, Gaussian is a natural guess for this, and it is in fact ground state. So consider the function, let's call it wave function, psi naught of x equal to e to the minus x squared over 2. Okay. Clearly, q acting on psi naught of x is dx x acting on e to the minus x squared over 2. The first term pulls down a minus x. Factor of 2 cancels off that factor of 2 and leaves you the exponential. The second one gives you an x multiplied by that. So indeed, this is a 0 mode. So this is a 0 mode of q dagger q. That's because if I act with q on psi naught, I get 0, and if I act again with q dagger on that, it's 0. Okay. However, the operator, I'm going to leave this as an exercise for you guys, to show all you that the operator q dagger does not have a normalizable zero mode on the set of square integrable functions of the real line. That is to say, I can come up with some, I can cook up a wave function that will satisfy the equation minus d by dx plus x on that wave function equals 0, but I will find that it is non-normalizable on the real line with respect to cinema. All right, so how do we go about solving using this information, in particular this information, that this is the 0 mode, to solve the harmonic. Okay. Well, if psi naught is a 0 mode of q dagger q, this means that if I act on psi naught with the Hamiltonian, that's just q dagger q plus 1 acting on psi naught, which is just psi naught. In other words, this 0 mode of q dagger q is an eigenfunction, it's an energy eigenfunction of the Hamiltonian with eigenvalue 1. Yeah? Agree with me? So this is an eigenfunction of the Hamiltonian with energy eigenvalue 1. Okay. In whatever units we want. But h was also Q dagger minus 1. Right? So H acting on the same psi naught, or Q dagger minus 1 acting on psi naught, was also giving you psi naught. Well, this means that psi naught, because it's a zero mode of Q dagger Q, it's going to be an eigenfunction of Q dagger, but eigenvalue 2. Everybody with me? So Q dagger acting on psi naught is Q dagger minus 1 acting on psi naught plus psi naught, which is H psi naught plus psi naught, which is 2 . So this is also an eigenfunction of Q dagger with lambda 2. Well, what that means is that Q dagger psi naught must be an eigenfunction of Q dagger Q. So, if I act with Q dagger Q on Q dagger psi naught, that is the same as Q dagger acting on Q dagger psi naught. But Q dagger psi naught, we've just proven is 2 psi naught. That's 2 Q dagger psi naught. In other words, this guy, this combination here, is an eigenfunction with eigenvalue 2. Let me just summarize here. Let's use this. So Q dagger psi naught is an eigenfunction of Q dagger Q with eigenvalue 2. Well, that means that if I act with the Hamiltonian on Q dagger psi naught, that's just 3. That's just Q dagger Q plus 1 acting on Q dagger psi naught, which is 2 Q dagger psi naught plus Q dagger psi naught, which is 3 Q dagger psi naught. So again, this guy psi naught, which is a zero mode of Q, is the Gaussian, right? If I act with the Hamiltonian on psi naught, it is an eigenfunction with eigenvalue 1. I then act on psi naught on Q dagger. If I act on Q dagger psi naught, this new wave function here, which, if you want to make things a little easier, call this guy psi 1. That's just psi 1. Right, with psi 1 to dagger psi 1. So H psi 0 is psi 1. H psi 1 is 3 psi 1. Okay? And you can show recursively then in fact we can continue this game and psi n, which is defined to be q dagger to the nth power acting on psi naught, is an eigenfunction of the Hamiltonian with eigenvalue, energy eigenvalue, 2n plus 1. In fact, this solves the problem for us. But let me put it into a more familiar form. Right? To put it into a more familiar form, notice the following. This operator Q, dagger, which was this minus d by dx plus x, I can write it in the following way. I can write minus d by dx plus x as minus e to the minus x squared over 2 d by dx of e to the x squared over 2. So yeah. Like that. I'll leave it for you to show that the two are the same. Again, the way you do that is by acting on the left hand side and the right hand side on some test function and keep track of your derivatives. Well, this means that I can write this psi n of x in the following way. It's minus 1 to the n e to the x squared nth derivative e to the minus x squared all acting on e to the minus x squared over 2. This guy here is nothing but a representation for the nth Hermite polynomial. That's it. That's the solution of the harmonic oscillator equation. We did not have to solve the differential equation. We gave a representation of the solution in terms of Hermite polynomials by just recursing to this operator algebra. It's a non-trivial amount to take in, so I'm going to leave this here and I'll give you a week to think about it. That week, I'll make sure that we don't have any lectures. Think about this. Thank you, David. And we'll pick up again next time, where we will talk about what happens if our operators on L2 are not normalizable. Okay. In which case we will have a continuous spectrum. If the final story for a continuous spectrum is different from the story that we're building here. Put these things together and talk about the more general picture of mixed operators of mixed spectra we discussed now the Hamilton. Yeah. Could you upload notes? Oh yes, yeah. Thanks. I'll do that. Welcome back.